Hello, welcome to week 2 material or week 2, week 3 material on PCA analysis and factor analysis. So today I'm going to cover the importance of why we transition from understanding linear regression to principal component analysis and factor analysis. And one of the reasons is from the discussion that we had last week in regards to overfitting and multiclinarity. So what happens in a situation when we have data where we have a lot of variables that have high correlations or high VIFs and they share a lot of information? In some cases, it's okay that we can cherry pick which variables to keep in the model that makes sense from a clinical perspective or from a domain perspective. And other times it happens that all these variables are really important together. And so, what do we do if we want to keep as many of those variables in the model, but also have to minimize the multiclinarity and the VIF and the overfitting? Well, one of the options outside of using lasso regression is to use principal component analysis and factor analysis, which will combine these shared variables into a smaller grouped variable. So if we have 25 variables that all share a lot of information together, we might be able to reduce them down to 5 grouped variables with keeping that shared variation, but having those 5 variables, those new 5 grouped variables, no longer be correlated to each other or very minimally correlated to each other. And so that's what principal component analysis and factor analysis, the overarching goal is to take all that shared variance and try to reduce it down into usable variables that we can use as standalone project tools, or that we can also use to put back into regressions and meet those assumptions that we talked about the last few weeks regarding linear regression. And we'll get more into those assumptions later on. So in order to better understand this shared variance of the principal component analysis and the factor analysis, we need to go back to the basics. And that requires understanding variance from a basic perspective. So early on in an intro stats class, you probably heard the word variance. And we usually used it as a single variate situation where you had a mean that was the center of the variance. And then when we talked about standard deviations away from the mean, that was talking about the magnitude of the variance. And then we moved on to other types of variances, as we discussed last week, with the covariances, right? The variances of the individual variables on the diagonal, and then off the diagonal being the covariances. And from the covariances, we can derive the correlations, which we understand to be the relationships and associations between two bivariate or paired variables, from which we can then, if we want to build upon this regression, have a simple regression with one x variable and one y variable. And then if we want to expand about that further, we can go into multivariate analysis, where we start looking at covariance of multiple independent variables. So one y variable to multiple x variables. And what we're trying to ascertain from that regression analysis is, can we explain or predict the y variable depending upon a research question? So correlated data, as we talked about from last week, if we have something that looks like this, we're having correlations that are positive direction because they're going from bottom to top, and they also seem to be strongly correlated. Remember, this is the IRIS data set with petal width on the y-axis and petal length on the x-axis. So the correlation at up here ends up being in the 80s or 90s, and see we're having a linear relationship with a direction of a positive nature and the magnitude of being of a strong nature because these data points are close together. But if we look at something like this, when we talked about the eigenvalues and eigenvectors, is we can take something that's correlated and by using this principal component rotation, make it uncorrelated, where it doesn't have any linear relationship to it. So if we look again at the data from the IRIS data set, we can see here that the correlations for the ones that we were looking about earlier are pretty highly correlated. So if we keep only petal length petal length, sepal length, petal width, we see that we have strong correlations in the high 80s to high 90s. And we can see that by looking at these scatter plots. So as we take another look at a three-dimensional look of this rotation of taking something that's correlated in a X, Y, Z plane, taking something that's correlated and making it uncorrelated, where this would be an X1 axis and an X2 axis, or a PC1 axis and a PC2 axis. If you want to look at how principal component analysis is done further, you can look at this website. We're going to be using other examples of data sets for principal component analysis and factor analysis. So the point of what we're doing all this is to get to the shared variances. And from those shared variances, we can find new axes. And these are the grouping variables that I was talking about earlier. So part of our process of the principal component analysis is to see how many axes do we need. And we're going to go through some subjective testing to determine how we do that. And then once we have the number of axes and determine what they are, then we need to figure out what they mean. And we're going to see this more through when we critique journal articles, as well as when we go to do the actual data sets ourselves. So when we take the variances, as we said before, the simple variances are the covariances with the variances of the individual variables on the diagonal, and then the covariances, so of variable 1 and variable 2 off the diagonal. And these simple covariances can then be converted into correlation matrices, where, remember, on the diagonal in a correlation matrix, it's always going to be 1, because the variable is always going to be strongly or directly correlated to itself. And then off the diagonal, we have the bivariate relationships, in this case of xy and xz, and then yz off the diagonal. So this whole point of the rotation last week was to get us introduced of what is required to make something that's correlated and make it uncorrelated. And we understood this to be through the eigenvectors and the eigenvalues. And so remember from last time, when we do this rotation, these axes are called principal components. And we need to solve for the eigenvalues that gives us the amount of variance. Remember, lambda equals 2. And then once we know the lambda equals 2, we can back into solving for the eigenvectors, which are going to give us the independent directions. So eigenvectors tell us where to go, and the eigenvalues are the magnitude of that. And as I iterated before, the PCA just simplifies this covariance matrix with these smaller grouping sets of variables that make it easier to understand from the older ones that have that multiclinarity and overfitting. So the next important part of understanding principal component analysis, now that we have sort of a foundation of the back end of how it works mathematically, is to understand what the application is between the principal component analysis. So principal component analysis is used in two different ways. The first way is dimensionality reduction. And this is mostly in the computer science realm, where you might be doing computer vision and you want to just reduce your features to remove the noise, like the background noise of your image or audio or whatever it is that you're doing. It could even be gene sequences. And you just want to reduce the features, and you're not worried about interpreting them because you want to just throw them then into a machine learning algorithm or something like that. So in that regard, in dimensionality reduction, we don't need to rotate, as we'll learn later on, because we're not going for interpretation. So because we're reducing noise, and hopefully there's more variance or shared variance than noise, we can keep a larger amount of variance in this situation where it's closer to 95, 99%. In addition, as we'll see in an example in a few more slides, we'll see that we can accept a larger amount of principal components because we're not going for purposes of interpretation. We're only going for purposes of we're only going for purposes of reducing features. And so this can be done for data mining, computer vision compression, imaging compression, audio compression, and also used towards, pre-processing for machine learning as well. So that is more of, just reduce and then move on. In latent variable discovery analysis, also referred to as factor analysis. And here, I don't like the use of factor analysis here. The common way that we hear it is latent variable discovery, because factor analysis and PCA analysis, as we'll learn in the second slide deck, are actually two different things. So in this regard, we have to be careful when we say factor analysis, when we say factor analysis, because the way that we arrive at a PCA analysis and the way that we arrive at a factor analysis is mathematically done two different ways. They have sort of the same goal and objectives, but they're done in two different ways. But with that being said, they are typically used in a situation where you have high multiclinarity. The end goal is to end up interpreting the results. And because you want to interpret the results, we have to keep things on a smaller scale. So parsimonious here is key, where a smaller number of components is better because it's harder to understand and interpret a large amount of components. And what is a large amount? It really depends. Typically, we use between 3 and 6 components. Some, depending on how many items and items are individual questions, let's say on a survey analysis, they would be, you could end up having 10 to 20 components, but typically we keep between, 2 and 6 components, sometimes 2 to 8 components. And as I just mentioned, a typical way that we arrive at this data is through survey analysis. But this data could easily be basic science data that you gathered through genomic sequencing. It could be data that you arrived at through a EPIC medical record or some combination thereof. It could be a combination of medical data and census data. And so it could be a wide variety of different things. But it does typically come from survey analysis, but it doesn't always have to come from survey analysis. The big key thing for both PCA analysis and factor analysis, when you're using it for latent variable discovery, is that you have to have domain knowledge. It gets back to when I was talking about the regression analysis and what variables to keep and what variables not to keep. A lot of that comes from having domain knowledge. And some of it you'll gather on your own as you work through years of working in the same domain. But a lot of times, a lot of that domain knowledge will still come from those front end users, whether, for myself, it's the faculty of medical doctors that I work with, or people in radiology that work with all the imaging, or, people that work in genomics and those types of things. So everybody has their own sort of domain, and you might have sort of a little bit of knowledge of each of those domains as you work more with these individuals in interdisciplinary settings. But for the most part, you will want the person, who is doing the open heart surgery all the time, or, is working with these different, variables, or actually collecting these variables to have a better idea of what's happening. So with dimension reduction, as I said before, when you're doing it just for reducing features, that happens a lot in the computer science machine learning domain. We're not worried about the interpretation, so we don't need to rotate. And this dimension reduction, when you're using it for a large amount of features, so let's say you have 100,000 genome sequences or RNA sequences and things like that. That is very good if you just want to reduce down those features, remove some of that noise or replication. That's a good way to go about it. So in this case, we have a compression image. If it's too old school, we have President Nixon here on the left-hand side, and on the right-hand side, we have Elvis Presley. And what they're trying to do with this image, it's a black and white image of 255 pixels. Each row is one variable or feature. So this image has 875 rows. And each row has 1,280 samples or features. So in this case, we are trying to compress this image to make it clearer and to reduce some of the noise, which a lot of times can happen more with black and white images than necessarily other types of images. So what we're going to do is we're going to take the scree plot, which you see here on the left-hand side, and we're going to try to figure out how many number of components we should be using. So remember, the eigenvalues is the magnitude of the direction. And that's going to give us an idea of how many components that we should use. Typically, what we're doing in a scree plot is we're trying to find the elbow here, where the number of components is going to be. So in this case, if we're looking at the scree plot and we're trying to see where this first elbow is, it might, look here like it's 4 components. But, as we get down here, there might be some subjectiveness as to maybe 4 or 5 components or something more than that. Maybe, 10 components or thereabouts. It's also a little harder to see because the scale here is so, the scale here is so large, they might be a little bit harder to see here as well. Now, there is a rule of thumb called the the Kaizen-Okenmeyer eigenvalue greater than 1. And so if we use the table function here, we can say lambda greater than 1. So that being the eigenvalues, remember lambda is for the eigenvalues. If the eigenvalues are greater than 1, say true, and then false, say 0. So 42 components have a lambda or eigenvalue greater than 1, approximately, and the remaining are false. And then if you say lambda greater than 1, you're subsetting out of the original data set those lambdas that are greater than 1, and you can see all 42 listed here. Remember that in principal components, as we'll learn later as well, the first component will always tell you the most information, as we can see from the lambda size here, and then it'll decrease as you go down the components. Now, if we look at principal components, for images here, we'll see that one component is very bad. I mean, this looks like a black and white Perry Mason, window curtain type of situation. You can't even tell what's going, what this is. If we do 20 principal components, we have an image, but this image is very blurry, even worse than if your glasses were out of focus, right? If we do 40 components, which is close to that 42 that we had with the eigenvalues greater than 1, we see that we have a better image than obviously with 20 components, but then we still have some blurriness, right, that we need to clear up here. We need to make this more sharper. Well, if we use 80 principal components, we have, as good of an image as we can here, where, maybe the remaining 20 components or whatever would be considered, the remaining components would be considered, noise. So in this regard, we'd say just to reduce the number of features, 80 components would be the right way to go here. Now, if we wanted to interpret 80 components, that would be way too large. So we have to keep in mind, are we using this for dimension reduction, or are we using it for latent variable discovery? So in this case, we're using it for principal dimensionality reduction. So in this case, it's okay to use 80 principal components. And as I said, because we're not doing it for meaning, it's okay that it's that large. We can throw away M components and still keep a lot of the shared variance. And as we saw earlier, it helps with the visualization to have those larger components. Now, let's switch gears here. Let's say we're not going for dimension reduction. Most of the time, particularly in the social sciences, in the medical field, but you'll even see with some of the articles that we cover in class, that it's used a lot in business and medicine, social sciences, and a wide variety of different fields. We use it for factor analysis or latent variable discovery. We're trying to show that underlying factors, trying to get that shared variance where we have all these all these variables having multiclinarity, and we're trying to reduce them down into more coherent and grouped shared variances that we can then use in model regressions or to further other types of analysis. And as I mentioned earlier, a lot of this factor analysis can come from a large variety of different data. It can come mostly from survey data, but it can be demographic data, census data, medical data, lab data where you're doing, genome sequencing or, taking tissue samples and all that jazz. So in this case, it can be used for a wide variety of different applications. And as I mentioned earlier, the first few principal components are going to give you the most information. So it's always going to be important to use the discrete plot and possibly the eigenvalues greater than one method to determine how many factors we need. And then once we have those factors, to interpret what they mean. Because in factor analysis, interpretation here is key. It is very important, and you're not using the factor analysis to just get variables. You're using them to get variables that make interpretive sense and are applicable to the field. So sometimes what we'll do is we'll also need to, once we have these interpretations, create raw scores to be able to further use the interpretation. So if you've ever taken a Myers-Briggs and they tell you, are you introverted or extroverted? Can you work well with people or not work well with people? They have taken 100 set of questions, which we call items on a survey, and used the factor analysis to try to group them. And then from those groups created raw scores. And so if you have a higher score on the introverted group variable than on the extroverted group variable, we might say that you're better working by yourself or being in a more autonomous situation than necessarily having to work in groups and being supervised or something like that. So we'll talk about those scores more later on, but let's first look at how we go about calculating them. So there's two functions that we use here. There's the princomp, or also the principal function, which uses the determinant. And then also there's the prcomp function, which is using a symmetric matrix and the singular values, meaning that you can find the inverse, are the eigenvalues. Now, the prcomp is more reliable, but unfortunately, it's harder to, the way that prcomp was written, it's harder to visualize that data. So typically what we do is we determine the number of components from the prcomp, but then use the princomp or principal functions to then get a nicer layout of what variable is within each of those group variables. So as I said before, prcomp is more stable and preferred. It uses singular value decomposition, where the princomp uses the eigenvectors and eigenvalues directly from the method using the determinant equation, something that we talked about similar last week with the rotation matrix. And so most of the time people prefer to use the princomp for visualization or the principal function for visualization, but determine the number of components from the prcomp. So let's see what that means. So if we're looking at an iris covariance matrix, we'll see here that the highest variance on the diagonal here is petal length. What does that mean? Well, within petal length, some of the length of the petals are really small. Maybe they're just growing. And then other lengths are really long. So if you have a petal that was just sprouting in spring, then it's just a little bud and it's slowly growing. But if this length petal has been around since the tree or the bush was around for 5 years, it's going to have a longer length, assuming they didn't get eaten by bugs or something or had weather erosion. Is going to be a lot longer than that leaf that just started maturing from this spring. So that's within petal length. But if we start looking off the diagonal, we'll see that these covariances then show that there's variances between sepal length and petal length. And so between, the horticultural differences between sepal and petal, there's variances in terms of how long those different types of leaves are. And then also even between petal width and petal length, right? Widths tend to be skinnier than lengths. And so there's going to be some variation there as well. So when we're using the IRIS data set on using principal component analysis on an IRIS data set, this is going to be a very, very simplistic principal component analysis. And for the most part, it's going to be highly uninterpretable. Well, it's going to be interpretable, but it's going to be very simplistic interpretation, meaning if we're only doing a principal component analysis on 3 variables, which is typically highly not recommended in the first place, we're going to get very small number of components, and those number of components may or may not make any sense. So let's look at this. So if we run a principal component analysis using PRComp, I've selected, subsetted out supple length, supple width, supple length, petal length, and petal width, and run a principal component analysis. These are the standard deviations for each of those components. Obviously, the largest component is going to have the largest standard deviation. It's going to decrease from there. This is our rotation matrix. That was the matrix we were looking at last week that had cosine and sines to rotate the data. And then summary P here is going to give us the importance of those components. So we're going to get these standard deviations, the same one that we had up here. We're going to get the proportion of variance. That's the individual shared variance for each component. So you can see principal component 1 has the most shared variance of 95, 96%. Principal component 2 only has 3%, give or take, and principal component 3 barely has 1%. And then if I add on to each of these, 95 plus 3 will give us, or 96 plus 3 will give us 99, and then add in 1 and we get 100%. All right, so that is the summary of the principal component analysis. Then if we run the summary P again, we get that same information here. And if we just ask for the rotation separately, P $ rotation, we once again get this rotation matrix. Now, the rotation matrix is not something that we're going to interpret. And actually here, this is just an example of how you come up with the formula for the principal component score. But in this case, we're actually not going to use the rotation matrix here. We're going to use out of the principal function, the rotation matrix. But this would give you an example of how you come up with the formula. You use the individual values here times the actual values that you get from these variables to come up with a raw score. And if we use just the first principal component, we would get 96% variance. So we're going to use an example that makes more sense, both from application and also from mathematics. So in this case, we're going to use the HBAT data set, which is going to be that data set that I mentioned earlier last week that looks at customer satisfaction. And so it used 10 other variables or so to try to explain customer satisfaction. But we're going to use it this week, not in linear regression, but to figure out how we can take those X variables that were highly correlated to each other and reduce them down into grouped variables that we could later use in a regression analysis. So we'll talk about more of that later. So first of all, when we want to calculate those raw scores, R can do that for us. And the PrintComp or principal function that we're going to use will ask for P-dot scores. And that's what we're going to be using through the lab in class and also for the R examples that I've given for week 2. If you're doing it through pre-RComp, you would use P.X instead of P scores. And we'll see that as we go through. And just to remember, we're taking data that had a lot of collinearity, as we see from the correlations here, and reduce them down with principal component analysis. And what we're seeing here is now these 3 principal components that they hardly have any correlations to each other. They're no longer correlated. So remember, petal length, petal width, and supple length were highly correlated to each other as individual variables. But when we reduce them into these components, and we haven't talked about how in IRIS data set, we probably only use one component. But in this case, when we reduce them down into these components no longer are correlated to each other. And so we could technically, if we wanted to, put all three of these components into a linear regression and try to use them in a model. Okay, so then with visualizing principal components, as we talked about last time in some of the earlier slides, we have an eigenvalue here greater than 1. And so in this example, how many eigenvectors here have an eigenvalue greater than 1? Okay, so it's like, counting to the center of a Tootsie Roll, right? 1, 2, 3, 4, 5. There are 5 factors that have, or components, that have an eigenvalue greater than 1. So if I was trying to figure out the number of components that I wanted to use, I could say 5 initially. We'll see that there's a lot of subjectiveness that goes into determining the number of components, because it's not only based on the mathematical, eye test here, but also if the way these variables group together on the 5 components makes sense or not. And I'll have more examples as I talk about that through this slide deck and the second slide deck. Then we also look at the elbow here. And the elbow is going to be looking at where's this knee or elbow in the data set. So if I go and draw this out, we're going to play connect the dots. And excuse my art skills. Remember, I'm a mathematician, not an artist. So if we try to find the elbow here, we're going to get it around here as well, or maybe even around here. And so we might guess even 4 or 5 components here. So from the eigenvalue greater than 1, we have 5 components, but from the scree plot here, we have 4 to 5 components. And so in this case, we might start out doing a sensitivity analysis of 4 to 5 components, and then going from there. As I mentioned previously, these are sorted by the eigenvalues, and so go in decreasing order, with the first component always having the most variance or largest eigenvalue, and then decreasing from there. Okay, so this is the HBAT data set trying to predict customer satisfaction. But before we even would do anything with the customer satisfaction, we'd have to look into these variables. And it ends up that these variables end up being highly correlated to each other. So one way to get rid of this multiclinarity and try to keep as many variables here as possible is to run a principal component analysis. So when we run a principal component analysis on this customer satisfaction data set, the Read-HBAT data set, we're going to look at the scree plot here and see how many factors have an eigenvalue greater than 1. Okay, so 1, 2, 3, 4. 4 components. We also have here that if we look at the elbow or knee here, that we have 4 components. So we would say here that between the eigenvalue greater than 1 and the knee or elbow, the scree plot, that we'd use 4 components. Now there's actually 3 and 4 ways to get eigenvalues or eigenvectors to determine the number of components. And I'll talk about the 4th method when we cover the lab today in class. But the 3rd way is that we could say we want a specific cumulative proportional variance, let's say 80%, and then figure out how many components would give us 80% cumulative variance. So in this case, if we wanted 80%, there's 4 components that would give us 80% cumulative proportion. Why did I choose 80%? Well, for latent variable discovery, we usually want typically a minimum between 60 and 80%. Now, between the 3 different ways we've discussed so far, eigenvalues greater than 1, the knee, elbow, the scree plot, and the cumulative proportional variance, they all told us about 4 components. And we're going to see if that actually, next week, we're going to run this in person for a midterm review. And we're going to see, is 4 components really a good idea here or not? But at this point, based on the initial estimates, 4 components seems to be the good way to go here. Now, I hesitate to use cumulative proportional variance because everyone will start just choosing the number of components that give us a certain particular proportional variance. The problem with using cumulative proportional variance set limits is that while it works mathematically, when you actually come up with those combination of variables, it may not work in terms of the application of the variables making up this particular grouping variable do not make any sense together. And so in that type of situation can cause a lot of problems. So that is why, you can use this as sort of initial guess, but you're going to be a little bit more accurate using the knee elbow. And also sometimes the eigenvalue greater than 1 can also overestimate. So you want to use something in between the knee elbow of the scatter plot and the eigenvalue greater than 1. All right, so next steps for after you've determined the number of components is then what do the new variables mean? How do we interpret this? Because it's not just saying we have 4 components, it's what are the relationships between the variables in principal, the variables that make up principal component 1, what do they mean? Let's give them a name. And then once we have the relationship between all of these, we can then put them into a regression analysis. And then from that, able to compute raw scores and things like that. And we just recently had a paper published with my team from UChicago, actually using principal component analysis for social determinants. So once we finish the slide deck, I'll just show you an example of how that can be used in the medical field, in addition to all the other papers that we've looked at through class, or I provided for class reading for week 2 and week 3. Now, as I mentioned earlier in class, this can be used for a wide range of domains. You can look at this by looking for astronomy or geography and looking at planets and countries. You can use this in principal processing. So we use this a lot. If you want to take the computer vision specialization at DePaul, we do a lot of pre-processing with principal component analysis before we take those computer process features and throw them into neural networks or other machine learning techniques. Likewise, that can be used in medical imaging and processing, as ways to, pre-process before we do, other types of measurements, or yet again, put it into machine learning or other types of predictive models. It is very big in bioinformatics, using a clustering of gene expression data, using bioinformatics. It's originally used a lot in social sciences. So your sociology, your psychology, and that sort of thing, political science. But it also, as we'll see from the articles covered for this week in the material for week 2, week 3, that it also is dealt a lot in marketing and business applications as well. So how do we visualize these principal components? Well, the larger number of components that we have, it gets more difficult to actually do visualizations. But if we have smaller number of components, and typically we show these components in biplots, so 2 principal components at a time, we can use that using the biplot or the PCA plot. Now, the nicer visualization is the PCA plot, but it's not a built-in function. So you'll see in the lab that I will provide you the code to run for the principal component analysis that you'll have to run. This is back-end syntax that you run before you actually call it later on in your syntax file to be able to show the PCA plot for your data set. And the nice thing about the PCA plot is that it displays the contribution of each original variable to the principal components. Now, the biplot, the reason why it's not always the best visualization is because it'll show each individual data point as well as the eigenvectors. And so sometimes it can be a really messy visualization to see, particularly if you have a lot of data points and you also have a lot of factors or components, which then obviously makes it difficult to interpret. Also, one other thing about the biplots is because it's showing all the data points and the eigenvectors at the same time, it also can be very computationally intensive, as you'll see from the Young People Survey Lab that we do in class today. So the one question that we ask with the PCA plot is what variables are important and which axes are these variables important for? So the way that we look at this is using an XY system. So if we look at variable x6 here, we have that we're on the x-axis. So we're 0 for the x-axis. And then if we're looking at the y-axis, we're, around, other way around. This is 0.05 for the x-axis. And then on the y-axis, we're at 0. So in this case, we would say that x6 probably belongs to component 1 because the absolute value, if these would, because this is actually negative, but if we take the absolute value of each of these, 0.05 is larger than 0. And so x6 would belong more to principal component 1 than it would to principal component 2. Whereas x1 and x2 and x3 might belong more to principal component 2 than principal component 1. And then we could do the same thing with these variables as well. And we'd notice that for principal component 1, variables 9, 18, 16, 11, and sort of over on this side are more related to principal component 1, where principal component 2 would be variables up here like 12, 7, 10, and 13 would be variables that are more related to principal component 2, while these variables down here are related more to principal component 1. So part of what we're doing with this principal component analysis is, I've mentioned multiple times throughout the beginning of this slide deck, is that we want to take all these variables that have a lot of multiclinarity together and try to keep as many of these variables as possible, but reduce or eliminate this multiclinarity. And we do that through creating these principal components. And so remember, the way that we do that is through eigenvalues and eigenvectors. Eigenvectors are determined first. They give us the quantified magnitude of the variance. And the eigenvectors tell us the direction in which that magnitude should go. And then, depending on what we're doing, we might relax these requirements a bit. And that's why, unfortunately, a lot of people don't like PCA and factor analysis or any of these multivariate analyses methods, because a lot of it's going to be subjective in nature and not objective, but rather subjective. So rotating components. So what we'll notice from the next slide is that there's a lot of different types of rotations out there. The most common rotation is the Varimax rotation. And that rotation is assuming that your variable, or I should say your components, are independently or perpendicularly related to each other. Okay, so in Varimax rotation, we assume that the components are independent of each other. And that may be true or it may not be true. There's certain things that we'll have to do for checks before and after for principal component analysis, which we'll talk later about in the next slide deck, in regards to what variables are related to each other or not. And then the loadings here, those are going to be those intercorrelations that we're going to look at in a couple slides to get meaning from how these individual variables relate to the overall principal component that they are now a part of. So as I was mentioning, there's several different types of rotations, and this is just the most common ones out there. Varimax rotation, as I mentioned, is assuming that the variables are independent of each other. Well, what happens if these principal components are not independent of each other? What happens if they are actually dependent on each other? Well, if they're dependent on each other, then they're considered the oblique rotation, and they also refer to as the Oblomin rotation. So if they're dependent principal components or factors, they'll use the Oblin oblique rotation. Now, what happens if there are a combination of dependent and not dependent? Well, actually, before we get to that, let's say that we have dependent components, but we have a lot of dependent components or a larger data set. Then we can use the Promax rotation, and that's better computational power for that dependent situation where you have a large amount of data and also a large amount of dependent components. Now, sometimes what ends up happening is that you have data that is really sparse, maybe you have a few data points, or you have a very few principal components. And so in that case, it might actually be better to use the quarter max rotation. And this is more where you have a sparse data set. Now, I'm not covering it in this class, but there's actually a whole set of non-parametrics and also non-parametric principal component analyses where you have just complete sparse data, very non-normal, non-linear data. And so you can use non-parametric principal component analysis as well. As I said, this whole class is just using parametric traditional principal component analysis as you would see in most of your statistical programs, SAS, Data, SPSS, and R and or Python. But there are situations where you may need to use non-parametrics, but we won't be covering in this class. And then finally, the other spectrum is instead of having sparse data, you might have mixed data that is both dependent and both dependent and independent. And so in that case, we may end up using the Equimax rotation. But it's not very often used because it would be a rare situation where the application would require both sort of situations, where some data, you would have to be more like bimodal data, where some data would be dependent on each other and then other data would be perpendicular and totally independent of each other. So let's go back to that data HBAT reduced data set. We were looking at the variables that we could be using to predict customer satisfaction. So what did I actually do here? Where I created a temporary variable called P2 and used the psych library. And from that psych library, used the principal function, right in the data set HBAT reduce, which is only the numerical Likert scale variables that I showed you earlier. Rotate using the Varimax rotation. From the scree plot and those other initial tests and rules of thumb, we decided to start off with 4 factors. And scores equal true says, please calculate the raw scores for me. Now, keep in mind here that the raw scores here, if you use a data set that is actually scaled, these scores aren't going to be the raw scores, they're going to be the scaled scores. So just keep that in mind. So if this data set is actually a scaled data set because your variables were actually not normal to begin with, and in the next slide deck, we'll talk about the assumptions that we need to meet for principal component analysis and factor analysis. But if this was actually a scaled data set, your scores would be scaled here. If this data set is a raw data set without it being scaled, then these scores would actually be raw scores. So we chose a number of components to be 4 based on the eigenvalues greater than 1 and also the knee of the scree plot. And also, even when we looked at 80% cumulative proportional variance, it said to also use 4 components. So it seemed, to be that using 4 components seemed the right way to go. So we get these loadings, and these loadings are also referred to as intercorrelations. And so because you have the name in here, correlations, I forgot to see somewhere in here. Because you have the word correlations and intercorrelations, it just means what are these variables? What's the association or relationship between these individual variables and the components that they make up? Now, you'll notice here that we actually have an issue that we'd have to deal with, and that is this variable x11 here. We get what is called here a cross-loading. This is where a variable, in this case, variable 11, shows up on more than one variable, on more than one component. And this can't happen. So in order to correct for this, as we'll see in the lab, we may do one of 2 things. We may increase this cutoff value, and this cutoff value is only showing loadings here with cutoffs greater than 0.4, where the intercorrelations here or loadings are equal to or greater than 0.4. So in this case, we end up seeing that these are all greater than 0.4, but we may change this cutoff value and say, only include correlations that are greater than 0.6 to get rid of this correlation here so that, 11 would rightfully belong to component 4 instead of in component 1 or showing up in both component 1 and component 4. The more cross loadings that you have in your, when you run this principal component analysis, the more unreliable and inaccurate your principal component actually is. And so in that way, you would either want to, if you can, reduce the cut or increase the cutoffs, or you'd want to reduce the number of components. And maybe by reducing the number of components, you'd also reduce the number of cross loadings that you have. So here we see, remember, before rotation, these variables are all correlated to each other. And then after rotation, we try to make them uncorrelated so that they're more on the X, the Y-intercept and X-axes than sort of off of these X-axes and Y-axes. So this is the same principal component analysis that we were looking at before. Remember, we have this cross-loading here. But why is this important to talk about this cross-loading? Why is it important to correct for this cross-loading? Well, here we have 4 different components. So these variables have been grouped into the 4 components. So 9, 16, 18, and 11 supposedly belong in component 1. And in component 1 have complaint resolution, order and billing, and delivery speed. And so in this case, we might call this customer service. Remember, because each component has to have a name. So in this case, we'd say customer service, right? But product line doesn't really fit into customer service, which makes sense for if we increase this cutoff value to 0.6, that as we go down and look at component 4 here, if we include component product line in here, product quality, product line, competitive pricing, it's like the 4 Ps or, in this case it would be the 3 Ps. But in marketing, we actually call 4 or 5 Ps, product placement, price, people has been one that's been included in recent years. And so we get those, 4 or 5 different Ps used in marketing. Now, if I go back to component 2 and we do e-commerce, advertising, and Salesforce, in here, we might include something like e-sales or, e-sales marketing or something like that, so that we're getting into revenue, or revenue generating, something like that. And then if we get into tech support and warranty claims, this is the case where we try to not have another issue. We try to not have we try not to have 2 or less items in a component. So a good component will have 3 or more items. You can call them variables in a component. Okay, so in this case, when there's some rare exceptions to this, but primarily we always like to have 3 or more items in a component. So when we're looking at this from a domain perspective, we might say, should X8 and X14 be, in component 1? Do they make more sense in component 1 as part of customer service? Or is, this variable more logistics and this component more customer service? So, if you're in marketing or if you're in supply project management, you might have even better names for these rotated components. So the next questions that we get then is to rotate or not rotate. And as I mentioned early on in this slide deck, If we're just using dimension reduction, we don't need to rotate. But if we're going for interpretation, and the key here word is interpretation, we should use rotation. And that's to make the interpretation easier to understand. The other thing that we talk about in here is, what if we had one variable that was in miles and another in feet? Which one would have the greatest variance? Well, this goes to what if, is the differences really because there's two different units here, or is there a difference because there are differences across these different principal components and the variables within these components? So in that case, if we have different units of data, then we need to standardize the variables. And standardized variables is just another word for scaling. So if we have different units, and it doesn't even have to be miles and feet. It could be something is in liters and something else is in inches, or something is in millimeters and something else is in, cubic volume. So, cubic liters or, gallons or something like that. So in that case, before we run the PCA analysis, we'd want to scale the data if we're using different units. So what does that mean? Well, if we standardize or scale, we're taking those eigenvectors of now the correlation matrix instead of the covariance matrix. So if we're scaling, we should be using the correlation matrix. So the way that we scale is that in PRComp function, we'd use the option scale equals true to give us the correlation matrix. Or in the PRINComp or principal function, we use covariance equals false, which means that instead of using the covariance matrix, we're using the correlation matrix. So when not to scale, when all the units are the same. So if you're having a survey data set and all the data sets are in Likert scale from 1 to 10, that data is already all in the same units, so you do not need to scale. But if you have data that's Likert scale and some of the scales are 1 to 7, some of the scales are 1 to 5, those are technically considered different units. And if you're using things like age and BMI in addition to Likert scale data, those are different units. So you need to scale that as well. So part of understanding whether to scale or not is also understanding what is, what does each column mean from a domain perspective, and what are the units that are being used for each of those variables as well. Keeping in mind that, some variables might be in millimeters and some variables might be in centimeters. Those are two very different things. And so in that case, you would need to scale and standardize your data set. All right, so this concludes the end of the first slide deck. So before we get into the next slide deck, I have it up here. I just want to go over homework 2 with you as well. So homework 2 is going to be due Sunday, January 31st. So not this coming Sunday. So if we look at the calendar here, not this coming Sunday, but the following Sunday. So you'll have 2 additional weeks to cover this. And we'll cover it a little bit more next class as well, particularly since for those on Monday, we are not having class due to the holiday. So in this case, we'll have 2 weeks to for you to complete this, to complete this assignment. Problem 1 are sub-questions that are related to what we covered in the last slide, with the second slide deck of week 1, which is talking about multiclinarity and overfitting, and then also how those relate to regularized regressions and which regularized regressions we covered last week. Problem 2 is your final group project. And so in this homework assignment, I'm actually going to have you start determining which data set you're going to use. Well, first of all, who do you want to work with in a group? And we have about 20 students in the class. So your group size here is going to be 2 to 3 people. So I don't want your group to be more than 2 to 3 people. So 2 to 3 people or persons per group. Okay. Now, in addition to determining which 2 or 3 people you want in your group, I also want you to find your data set. Within that data set, tell me what's the specific field that that data set comes from. So what's the application that that data set comes from? I also want you to describe this data set. How many numeric or metric variables do you have? So how many continuous or discrete numeric variables do you have? How many categorical variables do you have? What is your sample size? And is this data set coming from merging of multiple tables, or is this just one table of data? Now, remember, categorical variables are variables like binary variables and 1 and 0, so like dichotomous or binary variables. But categorical variables can also be like levels of education, where you have multiple levels. So, you could have high school, bachelor's, master's, PhD, professional degrees, etc. Remember, for your data set, that you want at least 300 samples, and you want at least 15 to 20 numeric, continuous, or discrete column variables. Okay, so the sample size has to be at least 300 observations, and the numeric variables have to be at least 15 to 20 columns of numeric continuous data. And be careful, because a lot of times your binary categorical data is recoded into continuous data or into numeric data. So just don't look at, quickly look at the data set and say, oh, they're all numbers, so that's all continuous data or numeric data. That's not correct. Those numeric variables could actually be recoded binary and categorical variables. So please double check that. The other thing that I want to make aware here is that these data sets should be cross-sectional in time, meaning that outside of doing training and testing, where you'd have 1 year be the training data set and a second year be the testing data set, the principal component analysis and the factor analysis under the traditional method cannot mix years of data. So it should be data that is from one continuous year. And so don't try to combine, data from 2011, and try to combine repeated data from, 2011, 2012, and so forth. So that is the data set. So for problem 2, that's the final project. Let me see if I can erase this. Yeah, okay. So that's the final group project, initial assessment. I want you to figure out who your group members are, the data set, what field it comes from. So it could be finance, it could be MLB data, so like baseball data, it could be basketball data, it could be medical data. So whatever, area of specialization is interesting to you and your overall group. You might have to compromise, depending on who your group members are. That's why I ask you to do the class introduction, so that you can sort of have people that are interested in the same areas or fields, domains of interest as you are, to be able to have, sort of more easy groups to create. The other thing I want to also ask you here, and this is not steadfast, but also to make, to tell me what technology that you're going to be using in this data set, with this data set. So while I make you use R for the homework assignments, if you want, you can use Python, you can use SPSS or SAS or Stata to run these methods. You can also use Tableau and Microsoft BI and D3 if you know Java for visualizations. So you're not restricted to just using R for the final project. So just to get an idea of what people are using for the final project, it's a great way for me to sort of see, what people are planning to use, and if I need to help you out with using those methods in different programs, that will help me out as well. So then problem 3 is going to be your first critiquing of a journal article. And depending on how much time I have on this video, I also have in the discussion section under our tutorials, I actually have a additional video on how to critique a journal article that's strictly just focusing on how to critique a journal article. And so I'll make sure to include that link in this week as well, so that you can just use that link for critiquing a journal article if I can't get to it in this recorded session. So in this case, for the problem 3, I am going to just make 2 notes here. The first note is that question 1 and the first and last questions should both refer to applications. So I don't want the first and last questions to be related. I don't want the first and last questions to be answered in terms of statistics. I want them to be answered in terms of the application from which this article comes from. So this article is actually a combination of psychology, e-learning, and nursing, so the medical field. So in this case, I want this question answered sort of in terms of that realm of medicine and psychology and e-learning. So the first question, how are they applying the factor analysis? This goes to what is the research question and the application for which they are using this data set? The second question is, what kind of factor rotation do they use here? Is it Varamax rotation? Is it Oberlin rotation? Or is it something else? How many factors did they concentrate on in their analysis, and how did they arrive at the number of factors? So did they use 4 factors? Did they use 3 factors? And how did they arrive at that? Did they use the scree plot? Did they use eigenvalues greater than 1? Did they use, the cumulative proportion of variance? Did they use now I'm just forgetting the other one right now. Oh, no, it's forgetting me. I'll talk about it in the lab. It'll come back to me. So in this regard, how many factors did they arrive at, and how did they come up with that answer? So your usual answers are going to be scree plot, eigenvalues greater than 1, cumulative proportion of variance. And so in that regard, that's going to be answering question 3. Question 4 is explain the breakdown of the factors and the significance of their names. This is the one area where I'll actually allow you to do a screenshot of the table, but just don't give me a screenshot of the table. Make sure that you also explain what you're seeing in the screenshot. So are these accurate names? First of all, are the principal components or the factors in this case having names? And do those names make sense for the variables that make up these factors? In the next question, how do they evaluate the stability of the components? So in this next slide deck that I'm going to get to next, we're going to talk about factorability in terms of checking for assumptions of principal component analysis and factor analysis, which are KMO sampling adequacy, Bartlett's test of sphericity, which is looking at how much shared variance do we have or correlation we have in the overall data set that we're looking at. And then also reliability analysis or Cronbach's office. So do these variables make sense in the overall data set? Do these variables then also make sense in these new components or factors that have been created? Then the other question that we're going to get is, do they use these factors in later analyses such as regression? They don't have to use them in regression. They can use them in confirmatory factor analysis. They can use them as standalone, subscales for things. But how do they use these? They could use them in ANOVAs or other types of statistical testing. So how do they use these factors? Do they use them at all? Is this just the analysis? Or do they do further analyses using these new created variable factors? And then finally, what is the overall conclusion? What are the overall conclusions does the factor analysis allow them to draw? So, look at the conclusionary section or paragraphs, and what did they conclude from an application standpoint, not a statistical standpoint. From an application standpoint, what did they learn from running this factor analysis? Do nurses really, learn a lot from the e-learning? How does that change their psychology of attitude through e-learning? So, while the subset, data set or the subsample of the population are nurses in relation to e-learning, how does their psychology of attitude change in terms of what they're learning based on how they're learning? And so that's the overall conclusion. You have to then read through the conclusion and further explain, answering those questions. And then problem 4 is going to be a principal component analysis that you're going to have to run yourself. And this is using a psychology data set called the Big 5 personality test. And so this is a test that's used in personality. It's like a version of a Myers-Briggs but for personality, where it's going to teach you, based on how you group all these items, item questions together, and there's about 50 of them here, to group, what types of, each component will be its own personality, and you have to give that component a name, and then see if those variables make sense within that component. And obviously, does the name fit those variables? Now, this is very subjective. So, 5 people could look at these different components, and it could be 5 components, it could be more or less of those components. But you could have a wide variety of people look at these components, come up with different names based on what they're looking at. So yet again, it's very subjective. There's no right answer, which a lot of people, if you're in math, we know there's a lot of different ways that we can arrive at the same answer. But in this case, we actually might come up with different answers as well. So in question 4 here, in part A, remember we talked about different ways that we can come up with determining the number of factors or number of components. So you can use cumulative variance, you can use scree plot, you can use the eigenvalues greater than 1, based on whichever. So I'm going to ask you here to determine how many components would you use if you wanted a total variation or cumulative variation of 100%. How would that differ if I asked you to determine components from a scree plot? And remember, there's 2 ways that you can come up with components from a scree plot: the eigenvalues greater than 1 and the knee or elbow of the scree plot. Based on those 3 main ways of coming up with number of components, what do you think is the best number to initially start out with? So it is possible that each of those 3 ways will give you 4 components, but it is also possible that those 3 different ways will give you 3 different numbers. And so based on what you've looked at, what is your initial starting number that you want to use for a number of components? Then in part B, give me the formula for the first component. Typically, I'd ask you to do this for each of the components, but due to the situation and everything, just give it to me for the first component. At least for the first component. If you want to do each of the components, that's fine, but at least give me the formula for at least the first component. And then in addition to giving me the formula for how you calculate the score of the component, then give me the names of each of your components and an interpretation of what those components mean in terms of personality. Now, I'm not expecting you to be personality psychologists, but just using sort of your street smarts and your basic general knowledge, of, who would you like your friends, what type of personalities your friends have, or what personalities you'd like your friends have, or personalities that it seems that you feel that you exhibit or seem to favor, just based on that overall general knowledge of knowing yourself and knowing people, what are those variables in those components showing? And so give them respective names that way. In part C, I'm going to ask you to calculate the scores. I want you to figure out what's the highest score and the lowest score of each component. And we'll talk about that in the lab today as well. And then finally, in part D, based on the number of components that you use to run part B here, I want you to run the same number of factors. So you can do a comparison between the principal component analysis with 4 factors and the factor analysis with 4 factors, and see how different is the factor analysis from the principal component analysis when you're looking at the same number of components or factors. And is the interpretation different for the factor analysis than it is with the principal component analysis? So with that, keep that in mind as we're going through the lab, and also as we're going through the second slide deck in discussing, particularly for problems 3 and 4. So let's cover the second slide deck here. So in the second slide deck here, I'm going to talk about what is the difference now between factor analysis and principal component analysis. Now, factor analysis is another mathematical method for doing latent variable discovery analysis, which is one reason why I don't like calling, it's either latent variable discovery analysis or it's dimension reduction. I really don't like saying latent variable discovery analysis is strictly just factor analysis, because you can use both principal component analysis or this method of factor analysis for latent variable discovery analysis. So it can be a little bit confusing in terms of terminology, but factor analysis is similar in its overall goals to principal component analysis, because it is trying to reduce the number of variables to a smaller number of grouped variables that have the same shared variances, but that hopefully the factors are not dependent on each other. You just have shared variances within each of those factors, but not across those factors. And you're trying to describe in a concise manner the relationships among those components. Now, the main difference between principal component analysis and this factor analysis under the umbrella of latent variable discovery analysis is that in factor analysis, you typically have an underlying theory. So in that regard, maybe in sociology, you have a theory of deviant behavior, which you want to then test using factor analysis. Or maybe you have a theory of how personalities are derived and want to test that using factor analysis. So typically factor analysis will have an underlying theory that may not have been proven numerically, it may have or may not have, but there is a conceptual theory in whatever domain that you're testing. And now you want to test to see if you can prove it quantitatively, right, in an evidence-based manner, using numerics, using the method of factor analysis. And then there's 2 types of factor analysis. The one that we're going to be covering in class is exploratory factor analysis, also referred to as EFA. And this is the one where you have an underlying theory and you're testing to see if it works or not. And you're trying to sort of get initial idea of what's happening here through the initial evidence-based manner. This is descriptional in nature. I can't get to causality here through exploratory factor analysis. It's just sort of trying to see where these variables fall within the components, within the factors, determining the number of factors, and then that interpretation of relationships between the variables and the factors of which they fall under. The second type of factor analysis is confirmatory factor analysis. This is also referred to as structural equation modeling, or SEM. And this is where you can't actually get to causality. or path analysis, where you can, in confirmatory factor analysis, you can actually get to A causes B, B causes C, or, B moderates how A causes C. You can get to that with confirmatory factor analysis or structural equation modeling. This is one of the most advanced statistical classes that you can take outside of hierarchical linear regression modeling. So in terms of advanced classes, you have multivariate statistics, which you're taking now, hierarchical linear regression analysis, and then the very sort of most advanced class that you can take is structural equation modeling or confirmatory factor analysis. So in steps of factor analysis, they're very similar to what we do in principal component analysis, where you're going to select and set the variables, either through surveys or experiments or medical records or however it is that you're collecting this data. You're going to prepare a correlation matrix, particularly if you need to scale the data. You're going to extract the set of factors from using the scree plot, the knee of the scree plot, or the eigenvalues greater than 1, or possibly the cumulative proportional variance, but typically through the knee of the scree plot and the eigenvalues greater than 1. Once you've determined those number of factors, you're then going to rotate those factors and try to interpret them. And so that's where you're going to name the factors, talk about the intercorrelations. And so, 5 and 7 sort of go together there. You may also want to compute the factor scores. And we'll talk about later in this slide deck how we go about interpreting those factor scores. How do we derive them, and also how do we interpret them? The most important thing about everything that we do, whether it's principal component analysis or it's factor analysis for latent variable discovery, is that these factors or components have to make application sense. They have to make domain sense, or we're not using them the way that they're supposed to be used. So with common factor analysis, as we said before, it's similar to PCA analysis, that we're trying to reduce all these variables that have shared variance and multiclinarity and try to reduce them down into groups that have unexplainable common variance. And so that's how we get into these common factors. So if we take that customer satisfaction survey and we try to figure out, do these components make sense or not, we're going to look at these loadings. But a big part of whether these loadings make sense or not is if the data is normally distributed. So way back in that last end of the first slide deck, we talked about should data be rotated or not. And so in this case, the data should be, if it's not normally distributed, it should be scaled before we go into rotating this data set. Now, a lot of this data, particularly when we go to use the correlation matrix, is based on the maximum likelihood of estimates. And that's what helps us calculate the eigenvalues that help us determine the number of factors, and then also help us derive the eigenvectors. So by using the likelihood estimate, we're creating an optimized search. That's what helps us to take those eigenvectors and sort them in descending order to tell us that, the first component or factor has the highest eigenvalue and is the most important. And then as we go through those eigenvalues and eigenvectors, the factors or components that are least important. So this is what I want you to do in problem 4 of homework 2, is to run a principal component analysis and run a common factor analysis. So you notice that in principal component analysis, we're using the psych package using the principal function. But in common factor analysis, we're also using the psych package, but now we're using the fact_annul function. And that is for factor analysis, where principal is for the principal component analysis. You'll notice too that in principal component analysis, we're asking for the rotation where it's Varimax or not. In common factor analysis, we're just running the factor analysis with the data set, choosing 4 components, and we're printing the loadings as we would before, but now we're using a cutoff of 0.4 and then sorting them. For some reason, I don't know how they created it, but their sort function actually doesn't work. So it won't necessarily sort these I think what they do is they sort the factors, but they don't sort the variables within the factors. Same goes for here. I think they sort the components here, but they don't sort the variables within the components. And as I mentioned previously, it's important to have domain knowledge to understand if these variables make sense in their groupings, and also to come up with appropriate variable names as well. The other important thing to note here is that this, yet again, is not a one and done procedure. I'm not going to just run one factor analysis or one principal component analysis. I might need to do sensitivity analysis to determine what's the correct cutoff level to use. Might also, particularly when we have cross loadings or multiple cross loadings, I might also need to determine what is the number of factors or components to use, as I'll talk about more in the next slide. So one of the projects that I got when I was doing my graduate coursework in statistics at Loyola, I was a statistical consultant for Loyola University Chicago. And so a lot of my work was helping students with master's theses and dissertations to actually help them run the statistics and help them from a mathematical standpoint understand how to better interpret their results so they could write up the results and discussion sections of their theses and dissertations. So one student that I was helping was running a dissertation for a doctoral dissertation on bullying behavior in middle school students. So this was for school psychology. And so in this case, the doctoral student ran it on 750 middle school students. Most of them were male, but it was almost relatively close to being male and female students, middle school students. And they used a comprehensive assessment, which was validated previously, and then added on questions to virtual or cyberbullying because they wanted to see if there was a difference between physical, verbal, and cyberbullying. Now, initially, with that being said, we had hoped for a 7-factor or 6 to 7 factor 6 or 7 factor solution where we could see how people were being bullied, whether you were the bully or the victim, from both the physical, verbal, and cyberbullying. And so if there were differences between whether you were a cyberbully or a physical, like aggressive, whether you like physically attack, or whether you like to be more of a bully using words or verbal. And then also the same for the victim. So, is there a difference between when you're a cyber victim versus when you're a physical victim and you have a black eye, or between verbal bullying when they're calling you certain names or, saying mean stuff about you or other people related to you. So in that type of situation, we were hoping for a 6 or 7 loading or factor solution. And as you can see here, we used SPSS, which is typically used in the social sciences. And the Kaiser-Meyer-Olkin KMO test, so eigenvalues greater than 1, said that we should have a 7-factor solution. But then when we looked at the scree plot, particularly using the knee or the elbow of the scree plot, they said 4 or 5 loadings or 4 or 5 factor solutions. So I ended up running a sensitivity analysis on 7, 4, 5, 6, and 7 factor solutions. We found that the highest loadings came from 4 factors, but while we had the highest loadings from the 4-factor solution, the 4-factor solution also had a lot of cross loadings and a lot of weaker loadings. And so it wasn't weaker loadings in this case is when correlations or intercorrelations are 0.3 or less. So if you remember from correlations, 0 to 0.3 is considered a weak correlation. 0.4 to 0.7 is considered a moderate correlation, or anything above 0.3 to 0.7 is considered a moderate correlation, and then 0.7 and above is considered a strong correlation. So while we had the highest loadings in the 4-factor solution, we also had a lot of those cross loadings. So we had variables that were crossing multiple factors, which makes it more unreliable and inaccurate. And then we also had a lot of lower loadings, which is also not helpful. And when you have weaker loadings, they can also affect about how directly are these variables associated with these different components and or factors. So due to all of that, we ended up deciding to go with 3 factors. And this is just a really big table. So it's 3 factors, and then the questions are just continued to the other half of the table. So in this case, we wanted to have, bully versus victim for each of these 3 categories, and it ended up coming up that we couldn't look at physical, verbal, and cyberbullying the way that we wanted to. It ended up coming up just, were you a victim of bullying, regardless of whether it's physical, verbal, or cyberbullying, which, in this case, there might be limitations as to, there might be differences between physical, verbal, and cyber, but either our sample size wasn't large enough, or there's just not enough difference. There's not enough shared variances to be able to break it out that way. And then also bullying, were you the bully? And so, did you threaten people? Did you call them names? Did you push them, and so forth? And then cyberbullying, now the cyberbullying is also interesting because we can't break out between whether you were the bully or the victim here. So this also could have some limitations here as well. But did you send hurtful messages? Did you receive hurtful messages? And so to try to decipher, what's the differences between victimization and bullying, and then also cyberbullying. And remember, this was done back, this dissertation was printed in 2013. It was completed in 2012. So, in those early years, I would say between 2008 and 2013, there was a lot of school changes in both elementary school and middle school, and sometimes even high schools, about zero tolerance of any type of bullying, whether it's physical, verbal, or otherwise. And cyberbullying was also becoming a very big thing because you started having AOL instant messaging and text messaging through all those previous decades. And so they wanted to see, how, if you were on Facebook and stuff like that, we're making mean messages and blogs and different shared websites and things like that. So as we talked about before, principal component analysis and factor analysis can both be used for latent variable discovery analysis. And while their overall goals are the same in terms of trying to take those variables with shared variances and reduce them down into components or factors with that are not varying across components or factors, they are calculated mathematically in the back end differently. So principal component analysis looks at all the variance, and all the variance here include shared variance, unique variance, and error variance. So principal component analysis, when we say it looks at all variance, it looks at the shared variance. So what do all variables share? But there might also be unique variances across variables, and then error variances. So if we take 100% minus the shared variance, we will come up with what's it doing here? So if we take 100% minus the shared variance, it's going to give us the error variances. So in that regard, it will only look at, it can also, and actually if we take also minus here the unique variances, we can back into the error variances. However, the factor analysis only looks at shared variance. So in this case, factor analysis are always going to have smaller intercorrelations because factor analysis only looks at the shared variances, where the principal component analysis looks at all three variances. Now, also keep in mind that factor analysis is also different from principal component analysis in that factor analysis typically has an underlying theory. So, if there's an underlying theory as to why people buy certain products and there's a marketing theory behind that, that might more, with that underlying theory, you're going to test it probably more as a factor analysis than you would as a principal component analysis. But keep in mind that in the back end, we're only calculating the shared variance in the factor analysis compared to principal component analysis, where we can look at all three errors, particularly the error variance. So knowing which one to use, principal component analysis or common factor analysis. Well, dimension reduction is only used with PCA analysis. But if we're going to interpret data, we can interpret data using either common factor analysis, particularly if you have an underlying theory, as I mentioned previously, or you can use principal component analysis. Now, we've talked a lot in the previous slide deck as to whether to scale or not scale. The important thing here is if you have data that is of different units. So if you're using Likert scale that's 1 to 5 and other variables that are 1 to 10, you're using BMI data and age and medical data, and you have data that's from medical images and also from lab values and then also from demographics. Those are all in different units. And so you need to scale the data before trying to run a principal component analysis or a factor analysis. Now, one of the things that always comes up is, what can we do with these components once we've created them? Well, we can use them as the factors directly, and this would be something like, creating a score, like a hospital score or a pain scale, or whether you're extroverted versus introverted. And those are using the factors directly. We can also use them as a surrogate. And so in this case, taking these grouped components or factors and using them as inputs or sometimes as outcome variables of regression analyses. And so you can take these variables and use them as surrogates. So instead of having all those variables that were highly correlated to each other, you would use them as you would use the components or factors in place of those multi-collinear variables. So if you have variables that are collinear to each other, you cannot put them into the same model. So you will remove all those variables, and if they're in a component analysis, you'll put those variables, you'll put the component variables in instead of the individual variables that you inputted into the component analysis. And we'll talk about, it'll make more sense when we look at the lab about what that means. And then we can also use a summated scale. And so this could be taking factors and combining them into a score. And this would be more like the hospital score, where we take, if you have a high score or a threshold score for these components, you get a 1. And as many components that you have a 1 would be your risk score of, being readmitted to the hospital, or having a higher pain tolerance, or, maybe having more of a positive attitude, or, less symptoms of depression or something like that. So if we select a surrogate variable, there's a lot of different ways that we have to consider. We have to consider the loadings from a mathematical standpoint. So you'd want to choose variables that would give us the highest absolute loadings if possible. We also have to consider domain knowledge. Does it make sense to include all these component variable, component group variables together? And if we do this in model building, we also have to make sure that we're following all model assumptions and things like that. And possible disadvantages is that, by aggregating the data, we might lose some error variance. We might lose some differences. And also that it might be difficult to choose a surrogate. So if we're wanting to talk about someone who has, diabetes and how that might affect them with cardiovascular issues, we can use BMI. We can actually use a category of glucose levels. We could also use the HC1AB. I always got that wrong. But outside of the glucose level, the other test for diabetes, and so there would be like 3 continuous variables that we could use to determine, whether someone has, high level risk of getting diabetes or not. And so which surrogate variable, the glucose, the H1, or the BMI, the body mass index variable, would we want to use? Or if it's a component, are there 2 components that are similar in nature to each other? Which one should we use instead or not? So we're also going to talk about factor scores. So once we come up with these components or factors, we can also, when we say, scores equals true, they will calculate the scores. Now, whether it's the raw scores or the scaled scores, we will come up with scores, and then we can use those scores as, cutoff values, or, whatever it is that we want to do to create that. So possible disadvantage to using factor scores is that it might work for training data, but when we go to use it for a new testing data set, it might be sensitive and having errors and, just not performing as well as it would with a training data set. Likewise, the factor scores may be difficult to interpret. So if our Likert scales are, discrete values from 1 to 5, and we get a score that's 3.4, does that mean that person's closer to to the Likert score of 3 or more to a Likert score of 4? And that could be something between saying whether someone agrees or disagrees, whether someone strongly agrees versus whether someone neither agrees nor disagrees, on a particular question or component. And then with summated scales, the same thing. You want to make sure that that you have the most relevant variables from a domain perspective. That it makes sense to combine these together. That you're reducing measurement error, not adding on more measurement error. And then also making sure that these summated scales not only work for your data set, but work on a wide variety of different data sets. And I'll explain that more when we get to the example that I did at UChicago that recently got published at the beginning of January. And so we have to make sure that these factors are not correlated to each other, that they're also reliable and valid. And we'll talk about how we check for factorability in a second. And then the operation of summing should make sense here as well. That, it makes sense. There might be a lot of different ways that you can create these different summated scales. And does yours make sense in terms of how you did it and the data set that you're using and the field in which that you're creating this scale? Because you might need to take into account domain issues as well as mathematical and statistical issues. So in order to understand the factorability, we also have to take into account the assumptions of factor analysis. And so in that regard, we need to talk about normality, the linear relationships. So think about the 4 assumptions of linear regression. Linear regression is the foundation to principal component analysis. So all those assumptions from linear regression are important for principal component analysis and factor analysis because they are also considered parametric methods. So parametric being they are highly related to normality. And so if you don't have normalized data, you have to scale the data before you can go using principal component analysis or factor analysis. You also have to look at linear relationships. So, do these variables have a linear relationship to the principal components and to the variables themselves? Factorability, and this is what I talked about earlier. The factorability is in 3 different ways. The Kaiser-Meyer-Oka and KMO sampling adequacy, the Bartlett's test of sphericity, and also the Cronbach's alpha that goes to reliability analysis. And we'll talk about those in more detail. Now, if you took a research methods course at any time at graduate school or undergrad, we talk about content validity and face validity, also referred to as internal validity. It goes by a lot of different names. But essentially what we're talking about here is, do all the variables make conceptual sense together? So do the variables that we're including for these components and these factors, do they make sense on a content level? Then when we talk, and we can check that internal validity by using factor reliability analysis or using Cronbach's alpha. And so at this point, we can say, with the factor reliability analysis, does it make sense as a whole data set? And then when we go to check individual components and variables, individual components and factors, do those individual components and factors make sense? Do we try it on a new data set and that factor reliability analysis still holds, even though all the questions are going to be the same, but when you're using a new data set, that's different people on how they're answering that data set. And so that can vary as well. And we can do, time analyses. We can test a baseline characteristics at time 0 as a training data set, and then test it again at time 1 or time 2 on that being our new data set, and seeing if we still get the same answers or not. However, using new data sets, using time points across time can be very expensive. So a lot of times, particularly in the social sciences where you might not have a lot of grant funding, and longitudinal studies are time consuming because you have to cover these patients over 3 to 5 years or however long. Usually it's at least a year. But some studies like the MESA study for cardiology have been looking at patients for over 30 years and also multiple generations of families. So in that regard, it can be very costly. And so if you're not able to receive grants or external funding, it can be difficult to do those types of research. So how do we do factor reliability? We're going to use Cronbach's alpha, and the functions that we can use in R are under library psych, the alpha function, or under library FMSB, the Cronbach alpha. They're going to do the same thing. They're going to give you a value that is like a intercorrelation or a correlation. So it goes between 0 and 1. And anything above 0.7 is a measure of consistency or showing a strong relationship between all of the variables. Now, we typically like to start off with a minimum of 0.7, but in the social sciences, when it's very hard to get those large correlations, a lot of times we might be looking at a correlation, minimum correlation of 0.5 and above, or sometimes even 0.4 and above. So just keep that in mind that this cutoff value might change depending on the domain that you're working in. So if we're looking at the customer satisfaction survey that we've looked at the first slide deck, we can see that these are all Likert scale questions from 1 to 10. And so if we looked at something like redundancy, a lot of times you might ask, they asked me 100 questions on the Myers-Briggs, but it looks like, the questions from 50 to 100 seemed like they were questions that were rephrased questions from 1 to 50, meaning that, they sort of just asked me the same question on 50 to 100, but just reworded it to what they said in, 1 to 50. So, in one of the questions on 1 to 50, they might ask you, do you like working with your boss? And then in, questions 50 to the 100, they might say, does your boss have good leadership skills? Or do you not like your boss? And so they might just ask sort of similar questions as to what's your relationship with your boss? So if I ask these questions individually, I might not get the full scope if I ask these questions separately versus if I combine these questions together, I get a clearer picture. So just looking at this again, if I ask in a single question, it might not give me a full understanding compared if I come to this if I come to this concept from several different questions, I'll get a fuller picture or understanding of what's going on. So this is yet again the customer satisfaction. And as a concept, it can be hard to measure customer satisfaction, and that's why we're asking it from a wide variety of different questions here. So in terms of diagnostics, we want to look at variance loss, and if this is even a good data set to even do principal component analysis or factor analysis. And so the two ways that we look at the variance, and if we have enough variance to do this, is Bartlett's test of sphericity and also the KMO measure of sampling adequacy. So typically, if we're looking at something from a latent variable discovery analysis, we want to have at least 60%, between 60 and 80%, and sometimes if we're lucky, 95% or higher. But when we're doing things with latent variable discovery analysis, it's simply going to be 60 to 80%, and sometimes even lower in the social sciences. So the one thing that we check is shared variance, and that comes from communality. And the communality is just the sum of the squares of the loadings. So if we take the squares of those intercorrelations and add them all up, that's going to give us the percent of variance captured in each of those components or factors. And so this is like a pseudo R squared for factor analysis or principal component analysis. So in order to check, is this data adequate or not? If we wanted to, depending on how many variables we had, and it would take a while, but we could do correlation testing, we could do t-testing. We could do f-tests and regressions. But we might not necessarily get to, not everything can look at multiple variables at the same time. So you might have limitations if you're only looking at pairs versus, all variables together. And then we also have to ask ourselves, do we have enough sample size? So rules of thumb from Chebnicek and Fidel is that, you have to have at least 300 samples, observations, or N, to be able to run an adequate PCA or CFA. Now we'll see in one of the articles that we cover in class that you can get away with a smaller sample size only if the variables are highly correlated to each other. But typically, since a lot of variables will not be highly correlated to each other, meaning having a lot of correlations above 0.7, typically we have to run a definite KMO sampling adequacy to see if we have enough sample size and the Bartlett's test of ferocity to see if we have enough variance to run this model, to run this method, the principal component analysis or factor analysis. So ferocity is asking, is there a principal direction? So essentially, do we have enough eigenvalues and eigenvectors, variances within those eigenvalues and eigenvectors to run this type of model? So you can see the formula down below here. It's taking into account degrees of freedom for error, as well as calculating in the population sample variance. And we're using a Bartlett's test of ferocity. It's going to use hypothesis testing, similar to the variances of f-test, which says, are all these variances equal to each other for the null hypothesis, or is at least one of these variances not equal to each other? And contrary to how we typically would do a variance test using the f-test, the Bartlett's test of ferocity is using a chi-square test. And so you can see the more complicated chi-square test here. And if the p-value is less than the alpha value, or the chi-test statistic is greater than the chi-square critical value, which is looking at degrees of freedom of k minus 1, which is number of columns minus 1, and typical alpha value of 0.05, then we're going to say reject the null to accept the alternative that, that there is that at least one of these variances are not the same, and we have enough variance to do this. So let's look at an example here. Let's say we're looking at that customer satisfaction survey. If we say the variances are equal, if we're trying to test this hypothesis test, we're going to use the library stats, Bartlett's test, Bartlett.test, and it's going to give us this output here. And the p-value is very, very small. It's less than 0.05. And so we're going to say there are differences in the variances. So that means we have enough shared variances that we should be able to run this PCA analysis on this customer satisfaction data set. Now, I've been talking a lot the last 3 weeks of class about rules of thumb with sample size. And they come from Chebnicek and Fidel, who are psychologists that do a lot of statistics. And you'll actually find out if you read a lot through statistics history, that a lot of methods were created by psychologists or improved by psychologists that did a lot of statistics. So statistics and psychology actually go a lot hand in hand from an applied perspective. So some typical rules of thumb that have been created and sort of summarized by Chebnicek and Fidel is that there's a large ratio of cases, so sample size versus columns, items. or variables. And so we typically like to use a 20-to-1 or minimally a 10-to-1 so that you have 20 observations for each column variable that you're adding into the model. So if I have 10 variables, I'd want between 100 and 200 I'd want between 100 and 200 samples for those 10 variables. So typically people will use 10 samples per variable, but if you want it to be even more conservative, to use 20 variables, 20 samples per variable. Sorry, I'm getting a little dyslexic there. Or you can typically just say, have a factor analysis, or to do, a half decent factor analysis, have at least 300 cases. To be sort of more in that moderate, more confident range, 500. And if you want to be absolutely confident, at least 1,000 cases. And as I said, it also depends on the correlation. So if you have more highly correlated data, you can actually use a smaller sample size. Now, something that's going to come into play here is if you have an initial sample size, but then you have missing data. So maybe not everybody wanted to answer every question on the survey, then you may have started out with 200 samples, but you only end up with 131, particularly if you're using list-wise deletion. And so the way and how how many missing values you have and how you treat those missing values may also affect your factor analysis as well, or your component analysis. So how do we check for KMO functions? We'll use library Scikit KMO dataset, or you can use library REDAS for KMOS, and that will give you the KMO sampling adequacy. And what does that exactly entail? Well, that is a combination of correlations of the entire variable to the component, as well as to the partial correlations. So, if I add these variables onto each other, I'm going to get partial correlations. And then all the variables together would give me the total correlation. And so the MSA score is very similar to a correlation or an intercorrelation. And yet again, we're looking at sampling adequacies of greater than 0.5 to 0.7. Now, reliability analysis and sampling adequacy can also give you overall, and it can also give you on an individual variable basis. But particularly when we talk about these scores, either for Cronbach's alpha or for the MSA score, the sampling adequacy score, we're looking at the overall score. So the overall score should be at least a minimum of 0.5 or higher. And I apologize, there's an ambulance. So what I'm saying here is that KMO sampling adequacy and the reliability Cronbach's alpha, we're going to look at the overall score. It would be, sometimes it's helpful to look at if there's troublesome variables that we might want to exclude. It might be helpful to look at their individual values. But because this is a grouping method, we're trying to group all these variables together and reduce them into in smaller interpretable chunks. We want to look at the overall scores. Okay, so that concludes slide deck 2 for component analysis and factor analysis. So now what I want to do with the time that we have left is go over the R lab for the young people survey to sort of give you an idea of how to go about this. So first of all, we have to install these packages if you haven't already. And remember, HMIS and Scikit are good for descriptive functions, but Scikit is going to be very helpful for all those principal component and factor analysis functions that we use as well. ggalley, ggplot, voplot, coreplot, these are all helpful in visualizations, as we'll see. And then Bartlett's test of sphericity and some of these other ones will be used for visualizations as well as for checking our assumptions. So I don't forget again, I'm going to read in all these libraries, and so we can see them all read in. We're going to set the working directory so that we can read our files from this file, as well as export out if we need to. And I'm going to read in a file that's called responses. It's a CSV file, so we're going to use read.csv. Header equals true means that the variables in the first row are going to be considered variable names and not data points. And the separator for this data set is a comma. And we're going to call this data set in our responses. We're going to check the dimensions. Mind you, I haven't checked for missing data yet. So at this point, they've collected data on 1,010 students and have 150 variables. Now I'm going to check the head to see if this data got read incorrectly. This is a survey. And so you can see all this data was read incorrectly. Some of it is categorical data and some of it's continuous data. And we are going to eventually have to subset out the numerical data. But before we do that, we're going to check the names. And we're going to see there's 150 variables and 150 names on here. And they deal with all sorts of things, from pets to behaviors and emotions and favorite music and movies and subjects and all sorts of things. And this was a survey asking students in a European nation, I believe it was Slovakia, what are their different types, answering, university students answering different types of questions. So now we're going to check for missing values, and we're going to use sum is.na. Remember, is.na is logic, so it's only going to give you true and false. But if you add up all the truths, which are ones, and sum them up, they're going to tell you that there's 571 cells of missing values. And as I mentioned in the previous weeks, to make it easier for us to all work together with the same data set, we're going to use list-wise deletion, which is just na.omit, create a new data set. We're going to double check that that new data set has no missing values, and we're going to get a 0 here. We're then going to talk for structure here and see, and here we see that some of these variables are factors, and then the rest of them are integers or continuous values. So I'm going to use names again here so I can figure out which ones are categorical and remove them. And I provided the column names here for your benefit as well. And then I'm going to create a new data set, one that's numerical variables only. And then I'm also going to create a subset of variables here. So these are going to include different themes based on the different groupings of questions here. And that's going to help with viewing some of the descriptive statistics, as well as we're going to use this data set for conical correlation analysis next week and in the homework assignment going forward with that. And so it helps out to have some of those common themes as well. So as I mentioned in previous weeks, one way to check normality is using Shapiro-Wilks test. Only if you have less than 1,000 patients or subjects. If you have 1,000 to 3,000, you can use Anderson-Darling test of normality. You can also use visualizations of histograms overlaid with normal curves or box plots and things like that. Or you can also use skewness and kurtosis. So skewness and kurtosis can be very subjective. And here's some rules of thumbs of how to do skewness and kurtosis. I typically like to either use Shapiro's Wilks test or Anderson-Darling test, depending on the sample size. And obviously, if I have a sample size that's greater than 3,000, I am forced to only use the visualizations of box plots and histograms and normal bell curves and things like that. So I'm not going to spend too much time on this, but I can check the descriptive statistics to see what are the means and standard deviations? Are the medians close to the means or not? Is this data normally distributed or not? You notice that after I deleted the missing values, we're down to 686 observations here. So we're still in that moderate to superior sample size here. We can also do GG pairs to check about how correlated are these data together. And I use just a smaller theme data set so we can just sort of see how to do that. And so you can see this is behavioral data. This is like personality and views and opinions. So you can see with it being social science, these would normally be considered very weak correlations. But depending on how we'd want to set up the correlation matrix here, or the cutoff values for these correlations, they might be considered even moderate or strong, depending on what we consider as the cutoff values here. As we talked about last class, you can use the GG save option to save this figure. This is being saved to my downloads. We can also look at box plots And so we can see here, if I just look at the personality again, we can see different box plots. If I move this out, we can see the names for each of these. So is there a difference between people who are workaholics, between those that work ahead versus those that procrastinate or don't prioritize their workload? And so we can look at all that. We can also see that there's some outliers here as well. We can check for correlations and multiplanarity using the core plot. You can see this is very messy because we have a lot of variables here and the variable names are very long. So this might not be very helpful. We can also look at the ggcore plot. This might be a little bit more helpful. Obviously, we need to expand this out. Now, while this is using a choral plot here, these names are very long, and so that might not be very helpful. You might even want to subset out specific variables even within this subset of theme variables to see that you could have a better understanding of what these all are. Now, the other thing that we can do here as well is that we can run correlation tests and calculate their p-values. And then say if their p-values are less than 0.01, which means that you're only allowing 1% of error, so these would be our extremes. We could say create an if else statement that if your p-value is less than 0.01, say true, otherwise make it false. And then we could sum these up and subtract from 1, 1 being the diagonal where it's the variable to itself. And these could show how many variables are related to each other. So dreams is significantly correlated to 11 other variables listed here. And God, or anything related to religion that's not atheist related or whatever, 13 other variables are related to God as well. So even though there's nothing really else religious here, decision making or judgment calls, keeping promises, those different things might be related to a faith-based component here, even though we're just talking about God. That's where domain perspective comes into play. So the next thing that we want to do here is look at the PCA plot functions. Remember, it's not a built-in function. So this is the back-end code for running PCA plot. This is not the call function. This is just the back-end syntax to make the plot call PCA plot call function work. So you're just going to run this all in, and then later in the code, we're going to run the PCA plot, which is going to use this to calculate the values on the back end. But before we do all that, we need to check our assumptions. So we're going to check for KMO sampling adequacy. And see, it gives you individual variables, but it's also going to give you up here overall variables. So we get an overall MS of 0.76, which is very good. It's above 0.7. We're going to check for Bartlett's historicity, and this is a very low correlation, which means that we have a lot of shared variance here. And sometimes when we have such shared variance, you can't even run cluster analysis on this. So the one problem that we have with this is actually that we have so much shared variance in this set of people that we end up having, when we try to run a cluster analysis to see how these students are different from each other, we found out that they're really not different from each other. And we have a hard time running cluster analysis on them. All right, so test for reliability. We have to run the Cronbach's alpha, and there's two ways that we can run this. So if we run the first Cronbach's alpha, it's going to give you, for each individual variable, it's going to give you raw, it's going to give you the standardized. And so you want to look at the raw here, and it's also going to give you a 95% confidence interval of the raw alpha. And so 60.62 is, let's see here. These differ on, yeah, so there should be a correction here. Oh, no. Yeah, so there should be a correction here. This should be 0.62. So here we get that the Cronbach's alpha is 0.62. Now, while we typically like to have it above 0.7, as long in social sciences, for this type of survey, as long as it's 0.5 or above, it still would be considered okay. The word I forgot in the previous slide decks is parallel analysis. So that's the fourth way that we can determine the number of components or factors, is using parallel analysis, which was created, not too surprising, by a psychologist called by John L. Horn in 1965. And this is as close as you can get to a heuristic, objective way of coming up with the number of components. It uses Monte Carlo simulation, where it tries to use the actual sampling, a lot of times the actual data set, to come up with an idea of what the theoretical solution would be if you were dealing with the population overall, as to the number of eigenvalues and eigenvectors that you should use for your number of components. So the way that you can use parallel analysis, and I'm just going to use it on the personality views and opinions, which is a small subsector of the data set. I'm going to use library psych fa.parallel. It might take a little bit of time. And if we zoom in here, it's going to tell us from where the knee is. They run it for PCA analysis as well as for factor analysis. Remember, PCA looks at all variances, shared, unique, and error variances, where FA only looks at shared variance. So it will give you a little different depending on which one you're looking at. Now, likewise, they use simulated Monte Carlo, and they also use bootstrapping on top of the Monte Carlo. And so that can also, that's how you're coming up with some of these confidence intervals as well. And here are the eigenvalues greater than 1. So whichever has eigenvalues greater than 1 would give you a wide idea of how many factors or components to use. Now, although this tries to be objective in nature, it also can be overestimating. And so I typically tend to use this as like an eigenvalue greater than 1 situation, and use it sort of between the knee and this and the eigenvalues greater than 1, as sort of a roundabout way. So like in this case, it's going to tell you to use 11 factors or 9 components. And when we end up going to do this for creating a PCA analysis, I'm going to run a scree plot with an alpha line. And it's going to tell me that all of these variables, it only shows the first 10. All these first 10 variables are correlated to each other and they have eigenvalues greater than 1. But when we go to look at the knee plot, it's actually going to show that 1, 2, 3, 4, 5, between 4 and 6 components might be the better way to go here. So I'm going to show you the summary in print PA. And here, this is where you're getting sort of the raw values. But it's a lot easier to look at in using the principal function. So we're going to look at that a little bit later. So in this case, to plot it, you could, here we just had the scree plot we just looked at. You could do PCA plot. Now this is where I'm calling the function PCA plot from the code that I ran in the back end at the beginning. And it's going to give me a PCA plot. Now the problem with this is that these variable names are really long. And it's going to show this data, all these names are going to cover each other. Now, if you want to show it without names, that might be helpful. And just use the variable, the variable numbers or something like that. That might help with this making this a better visualization. But altogether, there's a lot of variables here. They have long variable names. And so this can be as great a visualization as this can be. It can also be very cumbersome or not very informative. We can also look at the biplot. And in this case, if we look at the biplot, you can see the eigenvectors here, and you can see the individual points of each subject. As you can see, this is a very bad visualization because it's sort of, not able to clearly see everything. And so most people use the PCA plot rather than the biplot. Now, if you had a very small data set and a few vectors or eigenvectors, this might work out okay. Or if you were using it to talk more about outliers than necessarily about things that they have in common with each other, then yet again, that might be okay. So if you were only looking at, to show that, subject ID 448 is an outlier as well as some of these top ones above, then that might be, the biplot might be a good visualization for that. I'm going to skip this next section here, but this is just showing you how to change your raw scores in PRComp to an actual Verimax rotation loading. But because it's easier done in the principal function, it's just best to skip to just doing it in the principal function. So not to confuse you, we're using the principal function now to show the loadings that we're going to analyze and interpret and name. So again, using the personality views and opinions, rotate using the Verimax rotation, n factors equals 6, scores equals true, psych package equals using the principal function, data set, rotation equals Verimax, n factors equals 6, scores equals true, with printing out the loadings with a cutoff of 0.4 and sort the vectors. So we do that, and it's a very large data set with variables. So it ends up being here that we have a lot of variables, and we also might have some cross loadings in here when we look at here. But we see that these loadings are 0.4 and above. So we do have a lot of things that are coming up as correlated, but we do have an occasional cross loading here or two. Now, remember that this is also a subset of variables related to a specific theme. So these subset of variables only explain 30% of the variance when we use these 6 factors, when we use these 6 components. Now, we can use the ls function to see all the different commands that we can use in the PCA. The primary ones that we typically use, and you can see there's a wide variety of here, but if we want the eigenvalues, we use P2 eigenvalues. And this is where we can say, you know, table PT values greater than 1. And here it'll just say, you know, we have 16 eigenvalues that are greater than 1, because we might not be able to see all of them, you know, on the scatter plot or the scree plot, because the scree plot only shows the first 10. Then we can look at cumulativity, which is the shared variances on an individual variable level. And then we can also look at the rotated matrix. These are our cosines and sines, which help us rotate the correlated data and make it uncorrelated. To calculate scores, you're going to do PT scores. This will give us, this will subset out the first column of scores. And then you can use, there's 2 things we can do here. We want to check minimum and maximum score. So we can use the min function or the min and max function. So here we get the minimum is -2, the maximum is 4, or we can just use the summary. And the summary will give you the minimum, the maximum, the 25th percentile, the 75th percentile, the median, as well as the mean. Now, you'll notice, why is the mean 0 here? And this is because these are scaled data. And so scaled data will always have a mean of 0. And so these scores are not raw scores, they're standardized scores. Now, also, we'd want to do the rest. And so you create scores 2 through 6, and then you can use the summary function for each of those. Now, we'll talk more next week in terms of what these scores mean in terms of high and low, but you know, depending on what we named that first component, if it was saying that you were more positive or negative, then you know, a high score might be that you have more of a happy personality, and a low score could mean that you're more depressive, or you know, have more depression symptoms than, you know, happy or positive symptoms. And then the final thing that you'd want to do here is do a comparison between how does your PCA component analysis compare to your factor analysis. So you're going to run a factor analysis with 6 components, cutoffs of 0.4 and loadings, and do a summary. And then looking at these loadings for the factors, compared them. Now remember, they're going to have lower values than the principal component analysis, because factor analysis only looks at shared variance, and principal component analysis looks at all variance, the shared variance, the unique variance, and the error variance. And then the final thing that you can do is that you can look at this using LiveRoad Factor Extra, and you can look at some of these other visualizations as well. And it's not going to let me because the data set's too large. I think I need to resize my data set. Okay, so here you can look at the PCA plot. You can see this is even a little bit nicer where you get the contributions here. So the redder it is, the more the variable is contributing to your dimensions. And then this, if it's more aqua based, it has the least meaning or contribution. We can also look at the biplots. And this is just telling me that the variable names are really large, and so they're having a hard time showing them. So you can see it again, how it can be, even if we zoom out, it can be complicated to see how all of these look nicely to each other. So here's the scree plot. We can see, you know, this gives us a nicer way of seeing where the elbow is. So in this case, we might even want to use 3 or 4 instead of, you know, out to 6. We can also, the nice thing about this, do a look at use a core plot to see which variables give us the most contribution. And so short, you know, the ones that are darker and larger are the variables that are contributing most. This might also help us if we want to reduce the number of variables and only do that. We can also see which variables are the top 10 contributing. And that's just because I asked for the top 10. I can ask for the top 20 as well. But these are the variables in order of importance in terms of the ones that are contributing the most for component 1. And then these are the variables that are contributing the most for component 2. We'll talk a little bit, we'll cover this lab again more in person next week. But you can see that, you know, get started on working at homework 2 on that as well. So thank you for joining me. I know this is an abbreviated class, but since you have the day off, I don't want to give you too much to watch over this week. And we will be covering the journal article and this lab again next week in time for the midterm and covering a midterm review. That's the one last thing I wanted to cover. We will cover a midterm review next week, but if you want to get started, the midterm review is all material from week 1 to week 3. So just regression, principal component analysis, and factor analysis. The midterm is going to be a take home, so I'm going to distribute it out after class next week, and it will be due the following week after that. The midterm comprises a combination of short answer, problem sets, so you have 2 problem sets, one for linear regression, one for principal component analysis / factor analysis. You'll have short answer questions, and then you'll have, I don't think I do multiple choice. No, I think they're just all short answer. I will double check on that. But you have a problem set, you have a critical review article that you have to do. And then you have short answer, and then you also have the problem sets and 1 matrix. So you have to do matrix multiplication or matrix operations as 1 problem set. You have a problem set on linear regression. You have a problem set on principal component analysis and factor analysis. And then 1 critiquing journal article, and then short answers on different concepts covered from week 1 to week 3. We will do a midterm review in class next week to make sure that you have a better handle on the principal component analysis and the factor analysis, so that we can cover that in more detail, as well as reviewing stuff that we've covered for linear regression and regularized regressions and all that from week 1, week 2 as well. All right, so thank you again for listening. If you want to catch ahead in the critiquing of journal articles, you can also look at the R tutorials in the discussion section. And I'll also post that link again underneath this one for week 3, so that you can sort of be able to use that as a side step as well. We also will be covering critiquing journal articles in more detail next week as well as part of the review. All right, thank you again. Enjoy your free day or your rest of your week, and I'll see you in week 4.